Hey everyone, thanks for watching today, and we're going to talk about Kramer's rule. And to do that we're going to need determinants. But Kramer's rule solves a system of equations that looks like maybe a1x plus b1y is equal to c1, a2x plus b2y is equal to c2. And it does it via determinants. So I'm going to just cut to the chase here. We can construct a matrix out of this called the coefficient matrix by just listing in an orderly grid, oops, that should be 2, the coefficients. And then the determinant of A, which I will just be writing as absolute value of A, is you multiply down the diagonal and subtract multiply up the diagonal. So a1 b2 minus a2 b1. So this is the determinant. It's this handy formula, and we're going to come up with a reason we need that based on this system by actually just solving. So what we're going to do is we're going to solve for x. And to do that, we're just going to get it so y has the same coefficient, and when you subtract them, the y's cancel. So what that means is we're going to multiply the first equation by b2 and the second equation by b1. That'll make b1, b2 the coefficient of y. So the first equation times b1 is a1 times b2 is a1 b2 plus b1 b2 y equals c1 and b2, and then we're going to get a2 b1 x plus b1 b2 y is equal to c2 b1, and we're going to subtract these. So here we go, subtracting the equations. Let's collect the terms for the coefficients for x. So that's a1 b2 minus a2 b1 x. And notice here, this stuff cancels for the y. And then we get c1 b2 minus c2 b1. That's the right-hand side. So this is great. We have the determinant right here, and a thing that actually looks a whole lot like the determinant here. Now before we do anything with this, I'm going to also solve for y. So solve for y. And to do that, we're going to do the same thing we did for x, or rather for y, but with x this time. So we want to have the coefficient of x be a1, a2, x. So we have to multiply the first equation by a2. So plus a2 b1 y is equal to oops, I wrote that wrong. This should actually be, let's write it as c1 a2. And then it doesn't matter what order I write these in because of commutative properties. And then we also want a1, a2x. So we have to multiply the second equation by a1. So plus a1, b2, y is equal to c2, a1. And again, we're going to subtract. Same process as we just completed. The x's are going to cancel. The coefficients of the y are a2, b1 minus a1 b2 y is equal to c1 a2 minus c2 a1. And now what I'm going to point out is, in fact, this is not ideal because this is negative determinant of a. So let's multiply by -1. And all that's going to do is reorder these terms. Just swaps them because we're multiplying by -1, and it'll swap this side as well. And now you notice this also looks like a determinant. So this looks like a determinant, this looks like a determinant, and this side is a determinant. So this piece here, C1 B2 minus C2 B1, looks like this determinant. See what I mean? It's C1 B2 minus C2 B1. So it comes from a matrix that looks like C1 C2 B1 B2. And I'm going to call this matrix A sub x. So this is the determinant of A sub x, which is just this matrix, the coefficient matrix, with the solution column swapped in for the x coefficient column. Now, guided by that, just taking a look at this pattern for a moment, you'll see that the 1 is the first column. The number 1 here comes from this first column. So this is kind of backwards down here. That should be A1 C2 minus A2 C1, which these are equal because of the commutative property. So looking here, this y solution gives us A1 C2 minus A2 C1, which is actually just the coefficient determinant with the a's the same, but the b's are now the c's. Are now the c's. Whoops, that's a 2. And I'm just going to call that a sub y because it's for the solution y. And now what you'll see is this is just the determinant of a sub y. Make that look more like a determinant. Okay, so at this point, we could rewrite these equations. So I will. And that means we have the determinant of the coefficient matrix times x is equal to the determinant of this a sub x matrix, and the determinant of the coefficient matrix times y is equal to the determinant of the y matrix. Now, if this coefficient matrix is non-zero, so if, actually I'm going to swap colors really quick so that way this is easy to tell apart. If the determinant of A is not 0, then, oops, I don't need that either, then x is equal to the determinant A x over determinant A, and the y value is the determinant A y divided by A. That's typically what you think of when you think of Kramer's rule. Now, if the determinant of A is 0, then, well, what we have is 0x is equal to ax, and 0y is equal to ay. But funny thing, this is 0 equals ax and 0 equals ay. So we have two possibilities. Either these two statements are true and we have a solution, possibly, or they're false. So if ax's determinant or ay's determinant are not 0, there are no solutions. Whoops. There are no solutions. But if they are both 0, what you end up with is 0x equals 0, which is true for any x, and 0y equals 0, which is true for any y. Or if ax equals ay, equals 0, so if they are all 0, all the determinants are 0, then there are infinite solutions. So you can have one solution if A is not determinant is non-zero. You can have no solutions if the determinant of the coefficient matrix is 0, but AX's determinant or AY's determinant is non-zero. Or you can have an infinite number of solutions that satisfy either equation. What I mean by that is it's not just the whole xy plane, it's all x's and y's so that a1x plus b1y equals c1. But those happen to be the exact same x's and y's that satisfy the second one, because these are both lines and they're the same line in this last case. So there you have it. That's Kramer's rule from as intuitive of a standpoint as I can give you, which is it's just solve it for x, solve it for y, and see what you have. And determinants are a convenient language to write down that solution. Well, thanks for watching, and I will talk to you guys later.